Okay, welcome everybody. We're going to go ahead and get started. This is too much. You have found your way into the March Lowbrow meeting. Can't believe it's March already. I can't believe with this meeting. Didn't we just do this last week? Seems like it. Yeah, that also means I'm getting older, so. Anyway, I am Charlie Nielsen. Most of you probably know that, president of this club seemingly forever, but it's going to change someday. We also have a few officers here and probably online. We'll take reports from them later if they have reports to issue. But as tradition would have it, we always have our guest speakers speak to us first. In the event that some of you don't want to stick around for our lively and entertaining business meeting after our speaker. So if you do want to escape after that, we would understand that. And our speaker tonight is a repeat speaker we've had many, many times, and there's a reason for that. And that is Jim Shedlowski. Jim is a graduate of the University of Michigan. In fact, that was in 1960. And he has a degree in engineering physics. He spent 2 years as an artillery officer, which you might have noticed his hat, in the U.S. Army in Germany. And he worked for 36 years at General Motors as a vehicle development engineer manager, specializing in acoustics, noise and vibration, and retired in 1999. In his spare time, he wrote and recorded music for Epic and Roulette Records as one of the Ski Brothers. And I'll test your age here in the room. How many people remember American Bandstand? Jim was on American Bandstand one time, believe it or not. So upon his retirement, Jim rekindled a lifelong interest in astronomy and joined the Warren Astronomical Society. He's also a Lowbrow member, by the way. His interests include observing and outreach, and he owns several telescopes. But in recent years, his passion for astronomical history and technology has become a major focus. He belongs to a number of astronomy clubs in Michigan and Arizona, including the Lowbrows, which I'd mentioned, and is currently the secretary of the McMath-Holbert Observatory, the Astronomical Society. He has visited a number of major observatories, and in March of 2009, earned a certificate for observing 104 Messier objects in one night at the All-Arizona Messier Marathon. So it's my pleasure to once again bring back one of our favorite speakers, Jim Shedlowski. Use this or try it without it?
I think I'm supposed to use that.
Okay.
Thank you, Charlie.
You can flip that on.
Yeah.
Yeah, the problem is getting it where. And also, as you're going to discover, Jim is the only speaker that we actually get a song and a dance from at the end of his talk. Well, I lied about the dance.
Yeah, right. Can I get my slide mode here? Please.
Second, let's pull this out. It's like keyboard.
Yeah, well, yeah, sorry about that. Thank you, Charlie. By the way, just kind of coming back up here to campus is a little nostalgic to me. My wife has been on my butt to get rid of stuff. I just turned 87 years old not too long ago, and she wants me to get rid of stuff. So I've been going through pictures, 50 years of, maybe 60 years of pictures. And I ran across the one the other day of me standing in front of South Quad in 1954 when I first started school here. Yeah. Anyhow, good evening, ladies and gentlemen. Welcome to a presentation which I prepared 3 years ago and have recently updated. I picked up on a theme that I covered some 12 years ago entitled The Way We Found the Universe. That presentation covered the exciting period from the early 1920s when Einstein and Hubble revolutionized our understanding of the universe and helped out by the likes of Henrietta Leavitt, Vesto Slipher, George LeMaitre, and others formulated at that time the revolutionary Big Bang theory of an expanding universe with its island galaxies. Tonight's topic came to my attention when at a tiny library in Roscommon, Michigan, where my wife and I hang out, I found this slim volume, which caught my attention with a statement in its introduction. Quote, most of the articles gathered in this anthology were selected to capture the revolution that has shaken cosmology and our understanding of the universe in the last few years. So, with a statement like that and my cursory awareness of such things as dark matter and dark energy, my curiosity was aroused. This book's compilation of articles by noted astronomers and physicists essentially provided a primer on the controversies that have been going on in astronomy for the last few decades, the most momentous since the proposal of the Big Bang Theory in the 1920s and 30s. So after perusing a few other books on the subject, including one appropriately titled, quote, We Have No Idea, and being cautioned by Dr. Parton from the Warren Club that this would be a risky presentation topic, I decided to proceed with the research that has become for me a fascinating ongoing chapter in the history of science. I hope you'll enjoy my attempt to summarize for you the current turmoil going on in our understanding of the universe. In searching for an appropriate title, I was tempted by numerous articles in various publications, or by the title of a conference that I attended at the University of Arizona Stewart Observatory in Tucson recently, which implied a crisis, turmoil, or tension within the cosmology community. I finally settled on the less dramatic phrase above, which suggests that much of this controversy has been brought about by the largely unfulfilled quest for the nature and the properties of two mysterious quantities, which have been aptly named dark matter and dark energy. My presentation then will review the Standard Model of Cosmology, or which is sometimes called the concordance cosmological model, and recently revolutionary revised thinking regarding it. Let us first look at the general structure of the universe as it is now defined or described by the Standard Model of Cosmology. It is some 13.8 billion years old, and its observable diameter spans 93 billion light years. It contains over 10 million galaxies, each with from 10 million to 1 trillion stars. That's 10 to the 24th stars, or more than all the grains of sand on Earth. These galaxies are organized into clusters and finally superclusters, the largest gravity-controlled structures in the universe. Of the overall content of the universe, only 4.9% is ordinary matter, or baronic matter, which we can detect directly, with the rest consisting of 26.8% dark matter and 68.3% dark energy, both of which we know very little about, and which we will explore later. Since this standard model has been developed over the years with certain assumptions and theories, and then supported with ongoing observations and data, I'd now like to briefly review the history of our understanding of the universe as it was developed over the centuries in the Western world, from the early Greek philosophers through Copernicus, Galileo, Newton, Herschel, Hale, Einstein, Hubble, and finally to today. The earliest models of the universe came from the ancient Greek philosophers and then the Arabian astronomers, and are represented by Ptolemy's model of the universe, which were preserved in his book, the Almagest, which presented the Earth as the center of the universe within the sphere of fixed stars at a distance of 20,000 that of the Earth radius. This book was the authoritative text on astronomy for hundreds of years, and it was almost universally accepted until the scientific revolution of the 16th and 17th century, when the simpler Copernican sun model sun-centered model eventually took its place with the additional contributions from the likes of Galileo, Kepler, and finally Isaac Newton, who with his mathematical treatment of the laws of motion and gravity finally allowed a somewhat modern perspective on the solar system and its galactic neighborhood. Later in the 18th and 19th century, as the development of telescopes and other technologies progressed, the size and content and extent of the universe began to be questioned, as is illustrated by this next slide, showing William Herschel's 1811 chart of his observations of nebula and the distribution of them across the sky, and suggestions that they were something other than stars, along with Lord Ross's famous hand-drawn 1845 sketch of M51, the Whirlpool Nebula Galaxy. These hints of a larger and more complex universe were suggested and further advanced later in the 19th century with the arrival of photography, as with Isaac Roberts' famous photograph of Andromeda, the Andromeda Nebula from 1888. Still, at the end of the 19th century, our view of the universe was somewhat parochial in nature. The accepted model maintained that the Milky Way, our home, was the universe, and that it was about 30,000 light years in diameter with the solar system in the center. It further suggested that the common age of the sun, the Milky Way, and the universe was 20 to 40 million years old, and that the mysterious spiral nebula that were then starting to be detected were other planetary systems emerging, just as had our own solar system. Other viewpoints existed, but they were not mainstream until the first part of the 20th century, when a number of significant developments by individuals caused a momentous change in the way we understand the modern universe. This, quote, revolution in our concept of the cosmos, which I have classified as the early modern, involved a number of significant steps over a 15-year period, which combined to redefine the universe as we knew it. In 1912, Henrietta Leavitt's brilliant insight regarding the use of Cepheid variable stars as yardsticks or standard candles for measuring cosmological distances, coupled with Vestal Slipher's 1914 groundbreaking use of Doppler spectroscopy to discover that the recessional speed of spiral nebula was many times greater than that of any star, combined to give Edwin Hubble the tools that enabled him in 1925 to settle the 1920 Great Debate by establishing definitively that spiral nebula were in fact island galaxies. And then by 1929, to proclaim that the universe was expanding as governed by what we now know as Hubble's law. All of this was put into a revolutionary new mathematical framework in 1915 by Albert Einstein with his, quote, general theory of relativity, end quote. And then in 1917, Einstein published a paper entitled Cosmological Considerations in the General Theory of Relativity, in which he attempted to mathematically describe a universe which was static, as that was a common assumption of the pre-Hubble era. To do so, he was forced to introduce a term in his equations called the cosmological constant as a fudge factor to assure gravitational stability to his space-time universe. Einstein was challenged in this static universe assumption by several mathematician contemporaries. In 1927, an astronomer, mathematician, and priest named George LeMaitre reanalyzed Einstein's equations of general relativity without the static universe assumption, and found that it matched the expansion as announced by Hubble several years later. in 1931. This forced Einstein to recant and embrace the expanding universe and admit that the cosmological constant was, quote, the biggest blunder of my life. As significant as LeMaitre's use of Einstein's mathematics to describe the dynamics of Hubble's expanding universe was his insight that this implied that in the past it must have been smaller, and further, that at some point there had to be a beginning or an origin, a primeval atom that expanded to generate everything in today's universe. LeMaitre referred to this concept as, quote, the day without yesterday, end quote. The expanding universe theory had been born, although it would be almost 20 years later, in 1949, before British astronomer Fred Hoyle coined the name the Big Bang, in a critical put down of LeMaitre's theory. In spite of the acceptance of Einstein's mathematics, as interpreted by LeMaitre's model and verification by Hubble's measurements, the Big Bang theory did not immediately gain wide acceptance in the astronomy community. Critics pointed out that using Hubble's data for expansion, the universe would only be 1.8 to 2.0 billion years old, much too young for older stars, known to be up to 10 billion years old, or even the geologic age of the Earth. Others, conditioned to an eternal universe and cautious about the potential religious overtones, had a difficult time accepting any notion of a creation date. Several alternative scenarios were proposed to account for Hubble's redshift measurements, but of these, only one received serious considerations over the ensuing decades. This was the steady state theory, as conceived of and championed by Fred Hoyle, excuse me, and in the mid 40s. Hoyle's theory, which described an eternal, ever-expanding and continuously creating universe, which would accommodate Hubble's law and an interpretation of Einstein's general relativity, along with some other observational evidences. Its long-term resiliency was evidenced by a survey conducted in 1959, not that long ago, by the Science newsletter, which polled prominent astronomers as to their position on the theories. Of these experts, 33% favored the Big Bang, 24% preferred the steady state, and 29% were undecided or thought that both models were wrong. Sounds like this year's election. Among the early proponents of the Big Bang theory were many of the physics community who were busy exploring the revelations of the burgeoning field of nucleosynthesis. Einstein's most famous equation, E = mc squared, had finally conceived of a process for explaining the enormous energy produced by the sun and other stars. Developing the equations and conditions for the transformation of hydrogen into helium led George Gamow and his associates to calculate the production ratio of these light elements under conditions that would have existed in the Big Bang era. This ratio matched the measured ratio in today's universe, providing strong support for the Big Bang version of cosmology. Gamow further went on to predict that there should be a remnant radiation field that might be detectable, and that it should have a, quote, signature redshifted microwave wavelength with a temperature of about 5 degrees Kelvin. At this prediction, some 17 years before the cosmic microwave background radiation was actually observed, was ignored, was a monumental oversight due to the primitive state of microwave technology in 1948 and the inability of Gamow to convince their colleagues of its significance. Throughout the 50s and early 60s, the debate between the Big Bang and the steady state communities raged on, with Hoyle revamping his eternal steady state universe theory and inadvertently solving a problem that had stymied the Big Bangers when in 1957, he and his colleagues published a landmark paper which explained the synthesis of the heavier elements as products of stellar fusion and end-of-life explosions, or supernova, and processes not related to the birth of the universe. Particle physics and quantum mechanics had now become a serious partner of astronomy and integrated into cosmology. It would be 1965 when the next major chapter in the confirmation of the Big Bang theory's acceptance by the scientific community occurred. For you people who are in even close relation to my age, these are recent dates. So it's some of the stuff happened pretty recently. As mentioned earlier, in 1948, George Gamow and company had predicted that an artifact radiation from the Big Bang, which they called recombination. Their calculations had been based on the pressures, temperatures, and densities in the very early universe, as prescribed by running the expanding universe clock backwards. They had predicted that about 300,000 years after the Big Bang, the temperature of the universe would have cooled to about 3,000 degrees Kelvin. That'd be 5,900 degrees Fahrenheit. This would have allowed the free electrons to combine with the nuclei, forming the very first atoms, and would have emitted a sea of light, which might still be detectable. They had even predicted its microwave wavelength or frequency and calculated a redshift temperature measurement of about 5 degrees Kelvin today. In early 1964, Arnold Penzias and Robert Wilson, two astronomers working for the Bell Laboratories and preparing a large microwave antenna to do a sky survey of radio sources, were plagued by a persistent unwanted background noise in their system that seemed to have come from every direction. After months of effort to no avail to reduce or eliminate this noise, a casual exchange between Penzias and another astronomer at an astronomy conference led to one of the greatest discoveries in cosmological history. Further measurements and consultations confirmed that this noise problem that they had been struggling with for so long was indeed the cosmic background radiation, which had been predicted by George Gamow some 17 years earlier as an essential part of the Big Bang and not explainable by Hoyle's steady state universe. Penzias and Wilson would be awarded the Nobel Prize for Physics in 1978 for their discovery. A further property of this baby picture of the universe was the expectation that if looked at in more detail, there might be fluctuations in the radiation that could reveal additional information about the early universe. Over a period of more than 2 decades, this effort was undertaken by many researchers, including among them George Smoot. After many failures using high-altitude balloons and U-tube aircraft to minimize the effects of atmospheric water vapor, in 1992, Smoot was part of a team that was successful in using the COBE satellite to confirm its uniformity across the sky/universe, but also to measure tiny temperature variations of 1 part in 100,000, or 100,000ths of a degree in the cosmic microwave background radiation, which had major implications in our understanding of the early universe and its age, composition, and structure. For this analysis, Smoot was awarded the Nobel Prize in Physics in 2006, just a few years ago. The importance of the accurate measurement of the cosmic microwave background radiation, was of such significance that several follow-up satellite missions have followed the COBE, each of which have improved the resolution of these images and added further information to this ongoing primary contributor to the description of the Big Bang universe. The current measurements of the cosmic microwave background radiation are the most precisely measured spectrum in nature, with a redshifted temperature of 2.72548 plus or minus 57 thousandths degrees Kelvin above absolute zero, and fluctuations of 100 thousandths of a degree Kelvin. And this equates to an angular resolution of 1/12 of a degree of arc. These measurements, combined with other measures and incorporated into other aspects of the analysis of the Standard Model of Cosmology, such as particle physics and quantum mechanics and so on, and additional observations of galactic dynamics and content, finally secured the position of the Big Bang theory as the dominant description of the early universe among the astrophysics community. Some of the things it tells us is that our universe is 13.82 billion years old and was, quote, initiated from a singularity which imprinted its signature some 379,000 years later as the cosmic microwave background radiation, when the universe had cooled to 3,000 degrees Kelvin, which allowed the so-called recombination of electrons to join the hydrogen-helium nuclei plasma to form the first atoms. This allowed light to radiate throughout the expanding universe for the first time, which means you can't see beyond that. The pattern of the minute temperature variations in the cosmic microwave background radiation is believed to describe the structure of and the distribution of mass and energy in today's universe. Essentially, the cosmic microwave background radiation had ended the controversy between the Big Bang and steady state theories, but it had opened new controversies in the Standard Model of Cosmology. The question of how fluctuations in space-time had generated the enormous disturbance, energy, and mass that became the Big Bang universe from a singularity had by now become a mystery in the domain of particle physics and quantum mechanics, and some would say philosophy or religion. That continues to the present. Just as vexing as was how this singularity expanded to become the cosmic microwave background radiation detected as microwave signals 13.78 billion years later. The CMBR, cosmic microwave background radiation, presents, quote, a photograph of the universe when it was 378 years old, which we can now look back to and make ever more detailed observations of with sophisticated telescopes and instruments at various wavelengths. But it also presents a barrier beyond which we cannot gather electromagnetic data. The timeline of events surrounding the Big Bang event is currently postulated and accepted by the astrophysics community as follows. A quantum fluctuation in the balance of matter and antimatter in the space-time occurred at the beginning, the Big Bang itself, immediately followed by a period of time known as inflation, lasting some 10 to the minus 35th seconds, during which the universe expanded some 10 to the 25th time, faster than the speed of light, to a diameter of about 1 centimeter, during which time it achieved a high degree of homogeneity. After this amazing expansion, the universe continued to expand at about the current Hubble rate for some 380,000 years, to a radius of 42 million light years in radius, all the while cooling to a temperature of about 3,000 degrees Kelvin, as mentioned earlier, at which temperature the first atoms formed, the universe became transparent, and formed the baby picture of the universe that we now know as the cosmic microwave background radiation. Using this theory and calculations, at 1 second, the universe was about 10 light years in diameter in this scenario. From that inflation epoch or period, the universe expansion has continued for some 13.8 billion years. That's the visible universe, and now spans some 93 billion light years, usually known as the observable universe. The description of the origin, the history, and the development of the universe was the accepted version toward the end of the 20th century. The inflation theory had its critics, but since it addressed basic issues with respect to the overall Big Bang theory and was based on sound particle physics and quantum mechanics principles, it was the mainstream thinking. However, other issues had arisen in the observational astronomy arena. The observed dynamics of galaxies and galaxy clusters were exhibiting unusual anomalies. They were not moving as Newton and Einstein had dictated. In 1980, an important paper by Vera Rubin and Kent Ford revealed the results of 10 years of observations of the rotation of galaxies, which revealed that the velocity of stars and hydrogen gas was fairly constant, as measured radially from the center, instead of dropping off as it should have if it were governed by Kepler's laws with the visible mass of the galaxy. Some invisible attractive gravitational force was present. These graphs became known as Rubin's flat curves, and she spent much of her remaining career studying this phenomenon. In 1933, this same effect had been observed by Fritz Zwicky when observing the Coma galaxy cluster, where to explain its motions gravitationally, you would require 400 times more mass, he said, than was visible. He called this missing mass, dunkel matter, or Dunkelmaterie, or dark matter. Zwicky never followed up on this discovery, but the term dark matter stuck, and Rubin's work with it would have a profound impact on cosmology going forward. Rubin's work revealed that most galaxies contain 5 to 6 times as much of this dark matter and its gravitational influence as visible matter. And this magnitude caused the cosmology community to take notice. Something big was out there, and we couldn't see it. Its mysterious property of not interacting with any electromagnetic radiation or light meant that direct observations were impossible. However, by using its gravitational effects, by the early 1990s, dark matter's influence had been discovered throughout the universe, in halos surrounding galaxies and galaxy clusters. And using gravitational lensing and computing algorithms to map out dark matter, it was possible to visualize it, as is shown in this reconstruction, where dark matter is shown as a light blue haze surrounding the visible elements of this galaxy cluster. Further refinements have resulted in spectacular images showing the collisions of galaxy clusters, including this spectacular view of the so-called bullet cluster, which clearly reveals how ordinary matter, shown in pink, mostly gaseous in nature, reacts to the collision as opposed to the dark matter shown in blue. More significantly, in 2007, the Cosmos survey, using images from a number of observatory, including the largest survey ever from Hubble, the Hubble telescope, that's 575 images over 1,000 hours of observations, produced this 3D map of dark matter clumping in an area of the sky 9 times that of the moon, or some 5 times the volume of our home Virgo supercluster. And going back in time, halfway to the Big Bang. This study indicates that normal matter accumulates along paths with the densest concentrations of dark matter, and that dark matter clumping probably provides the seeds for the formation of galaxies and galaxy clusters. Quantitative survey measurements calculated that fully 85% of the mass in the universe was made up of this stuff that we couldn't see. Dark matter was real. It was important. It exerted gravity, and we didn't know what it was. And this really got the attention of the particle physicists. And with an increase of total mass of the universe by a whopping 85%, could the astronomers explain the effect on the expansion rate of the universe from this huge increase of its known gravity? By the mid-80s, one thing was fairly certain about the expansion of the universe. It might have enough mass density to stop its expansion and recollapse it, which was called the Big Crunch. Or it might have so little density that it would never stop expanding, or the Big Chill. But gravity was certain to slow the expansion of the universe as time went on. Granted, the slowing had not been observed, but theoretically, the universe was full of matter and the attractive force of gravity, now multiplied ×6, pulling all matter together. By this time, there was a strong feeling by both the astronomy and the physics community in the need to better understand the expansion rate of the universe over the life of the universe. We needed to look back in time to see how the expansion rate had behaved when the universe was much younger. We needed to look much deeper in space. Recall that it was Edwin Hubble who in 1929 first measured and announced to the world that the universe was expanding. He accomplished this by measuring the distance and recessional velocities of 24 galaxies out to a distance of about 2 megaparsecs, or about 6.6 million light years, by using Henrietta Leavitt's Cepheid variable stars as standard candles for distance and Vesto Slipher's Doppler redshift measurements for velocities. While Hubble's feat established the expanding universe and created, quote, Hubble's law and the Hubble constant, it was quite inaccurate and limited to the relatively short cosmological distances for which Cepheid variables were observable, about 60 million light years. The inaccuracies were later reduced by observations and techniques, but the distance limitations imposed by Cepheid variable visibility remained in place into the early 1990s. The Hubble constant, the slope of the distance versus the velocity plot of the expansion of the universe, had become the standard for measuring the expansion of the universe and other related parameters. The age of the universe, for example, is the reciprocal, or 1 over HO, the Hubble constant, or the reciprocal of the Hubble constant. So that's the age of the universe, going backwards in time. As originally defined by Hubble, its value was about 500 kilometers per second per megaparsec, which indicated a universe that was only 2 billion years old, younger than the age of the Earth. By 1990, when we could still barely measure distances outside of our own home Virgo galaxy cluster, The Hubble constant had been revised down to somewhere between 50 and 100, which gave a age of the universe of 20 to 10 billion, like 20 to 10 billion years, with still a great deal of uncertainty. With the precision satellite measurements of cosmic microwave background radiation beginning in 1992 with the COBE mission, an independent method of dating the age of the universe and deriving the Hubble constant became available. Later, with the other satellite measurements in 2001, Planck, and 2009, the Hubble constant value was inferred from the minute cosmic background radiation temperature variations using assumptions about the amounts of dark matter and neutrinos and other substances, and this calculated value for the Hubble constant was within tolerances of the direct observational values. But there was a general agreement with the revelations brought on by the discovery of dark matter that it was about time to pin down the value of the Hubble constant once and for all, and to see if it had changed in the last 13 billion years. Was the Hubble constant constant? A new standard candle was needed, which was much brighter than the Cepheids used by Hubble and his successors. There is a general consensus that the best candidate for a Cepheid class standard candle that was visible over much greater distances would be supernova, except for two problems. Number one, they are very rare and unpredictable. And number two, their luminosity standardization was questionable. Supernova are rare. They occur on the average about once in a century in our own galaxy, and their occurrence is not predictable. Fortunately, there are millions of galaxies out there to monitor. However, since a supernova event is transient, lasting only a couple of months, and unpredictable, detection, which can be accomplished with relatively modest telescopes, and then prompt follow-up measurements, which requires more detailed measurements by larger telescopes, becomes a complex logistical problem of managing the allocation of scarce technological resources, that is, observing time on telescopes, with short lead times and durations. In 1998, only, how many years ago would that be? 26 years ago, only 26 years ago. The National Science Foundation authorized $6 million for the establishment of the, quote, Center for Particle Astrophysics, end of quote, at the University of California in Berkeley, to recognize the connection of the very small with the very large in the physics versus astronomy world. The name of this agency might well have been, quote, the Center for Dark Matter, end of quote, as this was the motivation for its creation, along with the revelations from the cosmic microwave background radiation. One of the first initiatives of this new organization was to create a group to look deeper into the universe, further into its past, to try to see how much its expansion rate had been slowed down by this new gravity from dark matter. A small group of physicists and grad students at Berkeley's had been dabbling in an automated search and find system using a 30-inch telescope near campus and new computer technology, and by 1987 had bagged 4 supernova in nearby galaxies. This demonstration proved that their system could potentially automatically find more distant supernovas in quantities, given more resources. With the creation of a Center for Particle Physics, Astrophysics, this small group was given the resources and a formal charge to measure the expansion rate of the early universe using supernova as the new standard candle. With a name entitled the Berkeley Automated Supernova Search, or BASS team, they call it the BASS team, a formal assignment and expanded resources, Saul Perlmutter, and his associates began their efforts to develop an automated system to identify and classify deep space supernova and to validate a standard luminosity for them. By August of 1992, they had found their first deep space supernova, with a record redshift indicating it to be from about 4.7 billion years ago. Those physics guys actually had figured out how to do astronomy. They had developed what they called the batch method, whereby they would perform a wide field survey of a given region of the sky with as many as 100 observations over a couple of nights, encompassing tens of thousands of galaxies. Then 2.5 or 3 weeks later, they would resurvey the same region using a high-speed digital scanning search system to compare each of the photographs. They could quickly identify supernova candidates, which they then could immediately send on to larger observatories, which had been scheduled ahead of time for detailed photometric and spectroscopic study. The method guaranteed them to find at least a few supernova in each batch. They found out that they could deliver supernova on schedule. The second problem of luminosity standardization was at first a major problem, and that supernovas, the supernova 1As, which had been chosen as the most promising, seemed to have an unacceptable variability in luminosity. This problem was solved in 1933 by an astronomer named Mark Phillips in an almost Henrietta Lefferts fashion. He'd been studying the light curves of 9 nearby known supernova 1As and noticed that the shallower the descending slope was, the brighter was its intrinsic luminosity. Thus, while the supernova 1As did not have a standard luminosity, they could be calibrated. They could therefore be used as standard candles, bright enough to measure distances and velocities back to the earliest period of the universe. These supernova 1As have a luminosity which allows distance measurements some 500 times that of Cepheid stars. By this time in 1994, the astronomers had formed their own supernova search group, named the, quote, high Z team, end of quote, or the high redshift team. But they were 6 years behind the physicists, but with hopes of catching up with their, quote, superior knowledge of supernova and all things astronomical, end of quote. The High Z team was comprised of more than a dozen astronomers from 7 observatories and institutions and led by Brian Schmidt. Using their own version of the batch system and having access to a wide variety of telescopes, they quickly became bagging supernova on their own. So, by the mid-90s, there was a serious competition going on between the physics community, led by Saul Perlmutter, and the astronomers, led by Brian Schmidt, to discover how much the expansion of the universe was slowing down because of the huge increase of gravity from dark matter. By early 1996, the two teams were able to deliver supernova on any scheduled date with a kind of confidence that allowed them to convince Robert Williams, who was then the director of the Hubble Space Telescope Science Institute, to use his discretionary time on the Hubble, like that which delivered the Hubble Deep Field images, to use Hubble's high-resolution precision photometry and spectroscopy on a sampling of the very deep space supernova to augment their growing database. So in autumn of 1997, each team was busy analyzing their limited data sets, bolstered by several Hubble Space Telescope high precision measurements in their own unique fashion, to find the preliminary answer as to how much the universe was slowing down due to its increased dark mass density. By the spring of 1998, each team was interested in reporting their findings as soon as possible in an effort to be first. Both teams reached a similar result almost simultaneously, but there is a problem. The data revealed that the expansion rate was not slowing down, as was presumed, but was increasing, suggesting that the increased mass density from dark matter was being canceled by some anti-gravity repulsive force. Physics, or the BASS team's analysis revealed that the mass density required to slow the expansion of the universe was not only inadequate, but was deficient by 40%. The astronomer, or the high Z team's completely independent preliminary results came in a week later that it needed 36% too low in mass density. So 40% versus 36% was within the margin of error. These unexpected, amazing, and virtually identical results from two rival, competing, and completely independent scientific groups caused a major upheaval in cosmology that continues to the present. Preliminary conclusions have been reinforced and refined by much more data. The mysterious anti-gravity force, which has been given the name dark energy, and the mysterious anti-gravity force has been given the name dark energy. And Saul Perlmutter and Brian Schmidt shared the 2011 Nobel Prize in Physics for its discovery, after a decade-long feud about who was first. Dark energy, like dark matter, cannot be directly observed, but it can be inferred and therefore measured by its anti-gravitational effects on the visible large-scale matter in the universe. This new Standard Model of Cosmology since 1998, not too long ago, postulates that the large-scale dynamic expansion of the universe is controlled by a combination of gravity from matter, both regular and dark matter, and dark energy. The currently accepted values of about 5% of regular matter, 27% of dark matter, and 68% of dark energy suggests that the expansion rate of the early universe was controlled by gravity, and it was slowing down until about 7 billion years ago, when dark energy's influence began to give us the accelerated expansion we see today. And so, our knowledge of the universe as we now understand it, or don't quite understand it, has evolved over the last 100 years through a series of significant steps, starting with Hubble, Einstein, and LeMaitre's expanding universe and the Big Bang theory. Then came Gamow and Hoyle's postulation of the creation of elements by marrying the laws of particle physics and quantum mechanics to astronomical dynamics. This led to the accidental discovery of the cosmic microwave background radiation and its subsequent exquisite measurements, allowing the detailed modeling of the birth of the universe. The science of astrophysics had come of age. Then came the last 50 years of major, in some ways speculated and confusing and unexpected discoveries that have shaken the astrophysics world. First came Vera Rubin's documentation of a new source of gravitational influence which doesn't interact with light or radiation and dominates regular matter by a significant amount. We now call this material or quantity dark matter. Dark matter's presence created a new challenge to the astronomy, particle physics, and together the astrophysics communities. How did all this dark matter affect the dynamics of the universe? The quest for that answer, or to the answer for that question, became an interesting competition between the astronomy and physics community, which resulted in a minor revolution in astronomic measurement technology, but even more important, the discovery of yet another element in the control of the expansion of the universe. This time, the quantity was a repulsive force, pervasive in the universe, in amounts greater than that of all the gravitational attractive forces combined. We now call this entity dark energy. With a revelation from the cosmic microwave background radiation and the theory of inflation, and now dark matter and dark energy, the world of astrophysics has been revolutionized and is now in a significant state of flux. While our own understanding of the universe, its past, present, and future is much advanced over what it was 100 or even 50 years ago, we now have a number of major questions which remain to be answered concerning this dark universe. Some of these questions are, quote, what is dark matter? It may be as yet some undiscovered subatomic particle or not. Since it doesn't interact with electromagnetic radiation and we can't measure it directly, we really have no idea what it is at all. What is dark energy? It seems to be detectable only on large scales, galactic and larger, is a repulsive force, and that's about all we know about it. Is the Hubble constant really a constant? And what is its true value? The accepted cosmic microwave background radiation calculated value is not consistent with the directly measured value of 74 versus 67.4. This gives a difference in the age of the universe from 13.8 billion years to 13.3 billion years. The mostly accepted value at this time is the one from the cosmic microwave background radiation, which gives us 13.8 billion years. And number 4, what is the mechanism for inflation? What field or force could have caused the quote, faster than the speed of light expansion of the very early universe? Is there such a thing as an inflaton particle? Number 5, is the universe homogeneous and isotropic on the largest scales? And finally, and maybe most important, number 6, what came before the Big Bang? These and many other questions are currently hot topics in today's study of the universe and are commanding worldwide efforts to resolve them. These questions are the justification for billions of dollars being spent on programs like the LSST or Rubin Observatory or the James Webb Space Telescope. To quote the title of one of the books I mentioned earlier, the answer to these questions is, quote, we have no idea, but perhaps soon we will. I'd like to conclude by quoting some closing remarks from one of the books I cited earlier by Dr. Stuart Clark, entitled The Unknown Universe. One of his quotes was, quote, today, all our wishes would be granted if we could directly detect dark matter and dark energy, end of quote. And the second one is, quote, there are only 2 possibilities. Either dark matter and dark energy are real, and these vast reservoirs of matter and energy are just waiting to be found, or we have to radically rethink fundamental physics. Either way, we live in an unknown universe. And further, we live in an exciting time for cosmology. And now I'd like to add the final verse to a Don McLean song that I first rewrote in 2008 for a presentation entitled Astronomic Metrics, and then added a new verse in 2011 for another presentation called The Way We Found the Universe. And here's my final version of Starry, Starry Night. And I'd like you guys to try to sing along with me. Really? Because we're going to turn this microphone off, I think I was told. We're going to pick up from this microphone overhead. So you'll be going out to the whole Zoom world.
Move the camera around you.
Do their deep regret, I'm sure.
You have to excuse me, with my leg and back, I've not been able to stand up with my guitar much lately, so.
You have enough light, cheap?
Tell me when you're ready.
Oh, wrong way. I thought something wasn't right.
Starry night, looking at the Milky Way, so
View.
comprehend on the thought that galaxies shine from so far. We do not see them as they are, but as they were before this imagined. We try to understand the vastness of the universe in measurements, sometimes cursed, because it's so hard for us to know how distant is starry, starry night.
Zoom audience is seeing that. Sorry.
Hello. Testing, testing. Verse 2. Not so long ago, astronomers tried to explain with theories that were on their brain about what this bright nebula could be. It was modernized and instruments that measured well. They solved the mystery that tell nature of the silent galaxy. Or Hubble came along and found that blinking star to say Andromeda is far away, much farther than the Milky Way. That Cepheid is blinking still. Yes, it always will. The starry night contemplate the universe. Starts with a gigantic burst of energy that long ago that came to be from a singularity expansion that today we see cosmic radiation everywhere. Dark mass and energy are cosmic things we cannot see, which constitutes a mystery that we continue to explore. This universe has secrets still. We guess it always will. Thank you. And if we have time, I'd take any questions you got. I'm not sure I have answers, but
Dark audio.
there you go. Whoops. Any questions? I know I covered a lot of stuff and a lot of data, but
Are they thinking that whatever caused inflation might also be what's causing dark energy pressure?
no as far as I was able to discover, no, at this time, they're still trying to figure out the nature of this by getting better measurements than they have been able to do up to this point, because they can only use certain techniques and telescopes. The Hubble and the Webb are got high value time on them, so. As far as I know, no.
Thanks.
Anyone? Yes, sir.
Sorry, I am utterly unschooled in these things, but I did struggle with Krauss's book somewhat recently, and he seems to place a lot of stock in the metaphysical concept of potential, as nothing could come into being unless it had the potential to do so. And I wondered if you could comment on that.
I'm sorry.
Yeah.
Metaphysical?
Potential. Krauss, like the Leonard Krauss, I'm not sure.
Lawrence Krauss?
Lawrence Krauss. He talks about potential as a basic concept in the universe from nothing.
No, I guess I'm puzzled by much of this too, and I remember that somebody from the club here sent a email after the meeting was announced discussing some theories he had about what this is all got to be. There's a lot of people have theories that they're trying to defend about what dark matter or dark energy could be. It's a complete mystery though at this point. There's just no way to explain with current knowledge what these two entities could consist of. Anyone? Yes, sir.
Is space-time, what's the link between space-time and Big Bang theory? So did Big Bang create space-time or it existed?
Well, if we had Einstein here tonight, he might be able to tackle that. Well, I've always, one of the questions I had up on that last slide was, what came before the Big Bang? And of course, if you look at Einstein's theory, nothing, because time itself occurred at the Big Bang. So before the Big Bang, there was nothing. Now contemplate that. So we do live in an exciting time, and perhaps after I'm gone, 50 years from now, 5 years from now, whatever, we may know the answer to some of these questions, and I'd certainly like to be around. Or for my agnostic friends, I pity you, because I think going to heaven will get some answers to some of these questions.
You're doing pretty good for 87, Jim.
Anyhow, thank you all. Appreciate the audience, and thank you.
And Jim and I talked about a gift for him before the meeting, because we probably given him shirts and hats and everything else. As many times he talked, and he said it would be nice if we gave him a 1-year free membership. But I would like to see that and raise him another year and suggest that we approve 2 years free membership. What do you think? I assume nobody's opposed. What's that? Oh, we have lifetime.
I was gonna suggest 300,000 years was a first period.
We could go 300,000 years. The treasury would not be hurt by that. It's we have a motion to make it lifetime. Second, all in favor? Is anybody opposed?
Aye.
You are a lifetime member, Jim.
Might even be able to get signed up for another presentation next year.
Here we go. Sure, I can ask you about that.
You gotta bring some dark matter with you.
Okay. Get this thing situated, sorry.
Or I'm gonna grab one more of these.
Yes.
Yeah, they're still there.
Yeah. So, as far as what I have to report here, as I had said in my email announcing the meeting. We have more eclipse classes. But this thing's obnoxious. I can't stand the feedback. Anyway, so we have some of these. We also have these little ones without any earpieces. You just hold them up and look through them. And believe it or not, these are pinhole things. That seems like a pretty big pinhole, but I tried one of these and it seemed to work fine. So, and then we also have some more of the stuff that make a solar funnel out of that Don Foley has been offering. You can find instructions online and stuff for them. Projection material. And take as many as you want. It would be nice if I didn't take any of them back with me.
Where'd you get the whole from?
It was another Night Sky Network toolkit that came in, so. And also, maybe after the meeting here would be a more time, you can kind of look at this more. But I had mentioned last meeting that I got a call from the son of dear departed long-term member Bernard Freiberg, who was our observatory director, I think a vice president and newsletter editor for many years. And anyway, he had found some stuff. He was going through the house because they had sold his house and found these items. One of them is, you know, just a Wiltshire Sky Atlas. In fact, could anybody use this?
Got one.
Yeah, a lot of us have one. I think we have one at the observatory. If anybody thinks they could use this, it's yours. This other stuff is things like this book, Publications of the Observatory University of Michigan, Volume 3. Austin told me they do have these at the Bentley Library, but we have another copy of it here. And I'm really amazed. This thing still looks pretty good. And I looked at the date on it, it's 1923. And look at the shape of this thing, the condition. And there's also a bunch of pictures here. A lot of them are of the LeMaitre Hussey Observatory in South Africa. And a lot of them with the telescope that was moved there, which I believe Doug Nell told me was actually assembled outside here and then taken apart and shipped down to South Africa. Anyway, take a look at these if you're interested. I'm going to leave them here. And Austin's going to turn them over to the Bentley Library, seeming like that's an appropriate place for them. And they can preserve them better than any of us can. There was also, yes.
Will this talk be online?
Yes, it's being recorded. Yep. Yep. You're very welcome. Thanks for making it. Also, there was a set of blueprints for the McMath telescope. Austin has put those away for safekeeping, and we've requested if he can do it. If the Bentley Library would copy those, keep the originals and give us the copies, just in the event someday that they come in handy for something. Probably not, but it's kind of cool. Total blueprints for it. So anyway, after the meeting, if you want to take a look at some of this stuff, there's some real history here. In fact, somebody noted this newspaper that it's wrapped up in, which is falling apart, was from May of, well, the year fell off. Yes, 1932. Yeah. Thanks for remembering. Anyway, let's see. The only other thing I've got to mention is that it's election time. Next month, we have our annual elections. I have not polled the current officers to see who's interested in running again. I suspect most of them probably are. I think I'll probably, if you're willing, give it one more year, and then I'm going to start thinking about it. So I've been there before, kind of get burned out and then I get back, but at some point, I think somebody else should take this over. Maybe I'll find a vice president that would like to take over and I'll run for their spot or something. Maybe that way I'm still involved, but somebody else is president. We'll see how it goes. But anyway, and also Adrian has said that he does not want to run for president. And we've already had Ken Cook step up and say that he would be interested in taking that position. Ken was a previous vice president. So in fact, I'm going to officially nominate him right now if somebody wants to support that. Okay, so we got one candidate already. And you were saying something, Jim, that you're questioning that?
Well, as far as myself goes, I'm gonna be gone a good chunk of the spring and summer. And I'd like someone else to step up and do the things I've been doing as vice president. There's also other considerations that I have this year that it's a good idea to pass things along.
Okay,
So, you know, of course I'm available, of course I'll be a member of the club, of course I'll do stuff, but it won't be the level that I have
right.
until last year, so we need somebody to fill my piece of that.
Understood, Jim. So we have another vice president position open at least. Anybody here interested? Okay, I'll pull the membership, then we'll come after somebody. So, anyway, more on that coming, but it is next month. I think that's, I don't think has he said anything? I missed that, or?
I don't know, I know he's left black.
That is true. Yeah, he didn't say anything about the Lowbrows, so I don't know, but we'll find out. I'm gonna send an email, poll all the officers anyway. Brian Autumn. Yeah. He had said something about not running last time, but then he changed his mind and did. And I think he was concerned because he really hadn't contributed anything, but then he immediately did, so, but we'll find out. I think that's all I had. So we'll go to officers. Jim.
Like I said, I'm gonna be gone a good chunk of the summer. And my key to the hill on to reside somewhere among the officers or officers emeritus, so that the hill will get used while I'm gone. I won't be here for the April meeting. I won't be here for the April open house. Probably won't be here for anything going on in early May. And I may be gone in early June as well. So that's at the end of September is the Black Forest Star Party, and I'll be attending that. So there's a lot of stuff that I did last year that I'm not going to be doing this year. So someone else, if they would, you know, at least be a conservator for my keys. Don's volunteering.
How about that?
I will do the April 13th. I will be the open house coordinator for April 13th. Accepted.
OHC for April 13 and May 4. Much appreciated. Okay. Anything else, Jim?
No, that's funny.
Okay, thank you. Doug, our treasurer, sent an email to the officer saying he wasn't going to be present tonight. But as tradition, he will send in his report, so we have it for the newsletter. But he did say we still have plenty of money and all that. I think we're still at 199 memberships, but we'll see when he sends the report. Also, Dave Snyder said that he was not going to make it tonight, and he said he had no report. But if he had no report, isn't that a report? Anyway.
Only going to reflect people who had something to say. So.
That's true. And let's see who else we got. Jack.
You have to flip that back on from the screen. See y'all.
Take care.
Thanks again, Jim.
Where do I put this in? This is
I'll contact you about next year.
Go on this side.
Isn't that funny with USB sticks? You can plug them in 2 ways, but you can do it backwards 3.
It was just. Okay. So we throw this, it's on a PowerPoint presentation. Because this is going to be confusing to a lot of people. There it is. There it is. North Territorial. And have this in a minute.
Yeah, no, I thought it would have come off.
Is that content? You don't want that?
All down.
Well,
We're gonna, cause I can't.
I will figure it out here.
Yeah. How did we get, what's his name?
Sometimes I think we have too much technology.
Yeah.
Is the projector on?
I don't have a projector, sir.
Camera. Right, projector.
All laptop, that's why. So we want
Oh, that's what.
room PC.
That's got it.
Okay, all right, okay, all right.
And we discovered infinity.
Yeah.
Whoa.
Videos. Well, we should be able to share screen now.
That's pretty powerful.
What? Yeah, get rid of the. Oh, oh gosh. Okay.
Yes, I know. Yes, I know. And how do we start the?
Is that North Territorial looking west?
Think so.
Yeah, that's what I'm gonna talk about real quick.
Just trying to find the. Oh,
That's their thing. North Territorial.
never mind. Here.
Okay, let me go. Now, how do you go left and right? Okay.
Is
Keep
that
going way back. Okay, I'm gonna be real quick with this. First of all, what we're doing here. You are looking at North Dexter Pickney Road and North Territorial Road. And what's going on, some of you may have heard that Washtenaw County is repairing part North Territorial Road going into Dexter Town Hall. Okay, you will see this sign here. And everybody goes around it, and you can go around it too, because as you can see up here, right up here to the observatory entrance and that, there's no blockage or anything.
Yeah.
Look in the background, you see the guy driving his car out. Those are all the subdivisions along there, so they have to have a way to get out. Now, I'm gonna explain to you what else is going on. After you get past that, this is by Tolmer and Bard Road. Everybody goes around it and keeps driving to their home and that. So the area up to the observatory you can get to. Here's where the problem comes in. Now, as you're looking at this over here. Dexter Town Hall Road is closed at North Territorial. North Territorial stops there. You can see they got the Caterpillar out there, so like, you ain't getting through. Okay, some of you I know might live out towards Chelsea, and I used to drive down North Territorial to Chelsea. That's not gonna happen with Dexter Town Hill Road closed. So, if you live in that area, you might wanna just take 94 up to Baker Road and come up through Dexter. There's other roads, if you look at some side maps, depending where you live. But you're not gonna get through that. So that's done. So for those of you that come out that way, you're gonna have to find a different way. Now, here's the thing. April 13th is our first open house. As I showed you before, area up to the observatory is open. That's not a problem. The issue is other people driving that have to come out our territorial roads to bypass Dexter Town Hall. The other thing is our next meeting is going to be April 19th. And then that's why I wanted to bring this up today so people would know this. And then finally, supposedly according to Washtenaw County Road Commission, this is all supposed to be done by April 29th. Whoa. Yeah, I know, whoa. April 20, that's what it said on their website. So you can go over here. By that, yes, my Caterpillar will be gone by April 29th.
Yeah.
Yeah, because they're tearing that whole road out to do something, to redesign it, make it flat, get rid of that hill out there that caused an observing problem. There's a whole lot of reasons why they're doing this. But I'm doing this just so you're gonna hear the road shut down. Technically, at Dexter Town how it is, but you come up here, Dexter Pinckney Road, North Territorial, yeah, you can drive down through there. So you're coming up 23, take that to North Territorial, shoot all the way down. Or if you're coming out of Portage by Dexter Pinckney, shoot all the way down, make a right. You're coming up Dexter, make a left, you can go through. But I just want to let everybody know that, not to get too confused and think, oh, I can't go up because the road's closed. No, you can get out there, go there. So you see, here's the neighbors out here in the back. They're driving through there ready. So that's all I have to say about the observatory and everything that's going on. But we should be ready on April the 13th. That's all I have to say. Doc?
Yeah, I'll open house coordinator for the 13th.
Yes.
I will cancel it if it's cloudy.
Yes.
I'll also cancel it if I can't get enough support on Tuesday.
Okay, very good point. Very good point.
I'd also, if I have the key for that, I would do there's a beautiful clear night in the middle of the week. I would manage this. That's
Yeah. Okay. Yeah, that should be fine. I don't, according to the Wayne County, Washtenaw County, this part of North Territory should not be a problem for us to go to.
consider local traffic.
Yeah, local traffic, and that's what we are gonna be. And unless by some strange coincidence, you start work somewhere else on North Territory. They only have money to do this project, so that's kind of the good part to know. But that's the only money you got, and you have nothing else to do. That's it. That's all I have to say, but I wanted to let people know what was going on, so they didn't get disillusioned and think, oh, I'm not gonna be able to go out there, because you can go out there. We're gonna be open. With that, that's all I have to say.
Roads are expensive. We got a section on Jackson Boulevard in Scioto Township that needs some repair. I gotta check it myself because I didn't think it was too bad. With the road commissions, they gotta repair it. And it's a stretch of probably maybe 100 yards or something like that. $500,000.
Yeah. This thing was budgeted at over, I think, 1.7 or 2.5 million. Yeah. And the real reason they're doing Dexter Town Hill Road and everything with it is on a corner. They want to redevelop that corner with that old service station, that old store. And the other side, the guy's putting up 48 homes, and there's a whole subdivision coming in there. They want new turning lanes and that. There's been a big argument about redoing that road. And they came up with the money now. So anyway, that's what's going on. There's other things going on or other things. So that's all I have to say.
Thank you, Jack. Yep.
Goodbye.
Oh, it didn't like that, did it?
Oh, well, I guess not.
Oh,
Sorry.
okay. Quit the screen share. Now I can't find this.
No, I unshared it, but you have to switch it back to camera, alt in.
Oh, that's right. Ah, didn't work now.
In the video.
We have to. Oh,
Just switch that
there we go. Okay, thank you. Actually, you're the next person, Jeff.
I don't have a whole lot extra, other than we've been keeping up with people's pictures that are going onto the new website. We've been the photo gallery has been updated as they come in. There've been really some spectacular things, folks who come out. One interesting one is Edwin Hubble put out, redid one of his past shots. And he showed, he released the original one he had that he processed, and then he's been learning and playing with Pix Insight. And the one nowadays is spectacular. It's
Beyond awesome.
I take personal interest in it because he sold me the amount that picture was taken, so I now have possession of the ZEQ.
And you're gonna show it to us next month.
I'm not gonna bring the ZEQ.
Oh,
It's a lot, it's a lot of haul, but it's a good amount and steady. That was interesting. I did, in doing the presentation for next week or next month, I came across a whole lot of software that's free and freely available. And it runs on different platforms. And as I was putting together the presentation, I realized that's not a really good thing. So I'm going to try to put in maybe like the observing sections or something like that. Just put a survey of all the software that I've stumbled across and found either free or for a reasonable fee that does a good job. So that's probably an upcoming new section that came about because of the presentations. But anyway, it's going to be a challenging one to do. The scope next month is. I don't think there's anything other than that. We really haven't done much upgrading on the old website because we're kind of pushing toward the new one. We have renewed the lowbrows.club domain for the next year, and I think we've got 2 years left on the current hosting plan. So it's sticking around for a while, and whenever the university comes through. I did get an answer back on the AFS question, which is the storage that our web server uses, and they are indeed migrating away from AFS, but the web service that we use is not going to be changed. They're going to provide a storage solution, but it may not be AFS. So it sounds like they're trying to switch out the storage that's underneath the web server, and that those things may still continue, but enough is up in the air that I think going with the WordPress site, it's still going to be a better way to go. That's my take on it so far. It's nebulous, and the university moves very slowly sometimes.
Thank you, Jeff.
Yep.
Okay.
Yeah.
One more quick one. Just want to show this to the group. I'll remember that. It's the Ford Astronomy. Oh, okay, cool. Oh, okay. Okay.
Zoom out more.
Yeah, zoom out.
It's not showing on the Zoom.
There we go.
Okay, so we probably.
But anyway,
Switch to content.
guys, I don't know.
Sorry.
I just want to let them know about it.
There we go.
Oh, okay.
That's awesome.
What in the world? Oh, that's your mom.
Yeah, okay. Ford Amateur Astronomy Club's conference swap meet that they have every year. And it's still gonna be March 23rd. I just thought I'd let everybody know, because I know some people are interested in going. That's gonna be next week, the 20.
Yeah, next Saturday.
Next Saturday, 23rd. So it'll be at Henry Ford Community College, and you can go also their website, and they'll have pictures of it, stuff on there too. And you can see the drawing where you go and everything. So other than that, and it's the same place it was at last year, if you've been there. Last couple of years, it's been over here, come down the south center, the Mazar Administrative Service in the back. Yeah.
Plenty of parking there.
Yeah, you can park there, or you can park on the staff parking side or the back. So yeah, parking's not a problem. It's never been. There's all kinds of places you can park there. It's kind of fun. That's all I wanted to say. So. I don't Just wanted to make sure you remember, that's all.
Okay.
Hanging.
And that was pretty smooth.
Yeah.
Last but not least, I see out in the Zoom audience, our newsletter editor, Amy.
Hello, can you hear me okay?
We can do that.
Yep, nope, I don't have any report.
That was brief. Sure.
Got two things.
Okay.
Jeff, you blow a bean stacks.
Yes,
Thank you.
I suck, I'm motion that.
And has anybody been around long enough to remember Jim Newhouse, am I reading?
Yeah.
Yeah, house.
Yeah, they're the ones who did the hype ring, right?
Yeah, so I just wanted to let you know that Green Newhouse had a stroke and passed away.
Oh.
It's.
We were back at a meeting here when they were.
Yeah, they were members, in fact, they had already left Ann Arbor, gone up to wherever they were before I joined. But I knew them from the chemical. Just want to let you know.
Yeah, thank you.
Yeah. We're getting old. Some of us are getting. Not me.
Oh, before I forget, you might have noticed that they are running the observatory upstairs there, so if you're interested, go up after the meeting, check out the fence again. I think it's clear out there. I'm not. See, we're going back and forth, so. That not have seen anything, I guess, but does anybody have anything else? Hearing nothing, do I hear a motion to adjourn? Support. All in favor? See you next month.